Hi everybody, I noticed today that we were having a little bit of trouble with discovering the average atomic mass of our element beanium. So let's kind of retrace our steps. We started with a collection of beans and you needed to count the total number of beans, so however many there were in that collection. So you need to count those out. Then we separated those beans into their three component parts. We had the white ones, we had the black ones, and we had the red ones. So we need to count how many were the white, how many were the black, and how many were the red. So we're going to figure out our relative abundance, which is a percentage. So how many white beans were there in the total? And we'll multiply that by 100. How many black beans were there over the total? And we multiply that by 100. And how many red beans were there over the total? And we're going to multiply that by 100. So what these values give us here is our relative abundance. Okay, and that's a good word to know. All right, so what we're going to, if I spell it right, abundance. Okay, what we're going to get from that is a percentage. All right, so I'm just going to make up some numbers here. So let's say that 40% of my beans were the white, and I had 20% of them were the black, and then that would leave me with another 40% being the red. So my percents add up to 100. All right, so I've got my relative abundance. Now I need to figure out the average mass of all of those beans. So what I'm going to do next is I'm going to take, let me get rid of this. I'm going to take all my white beans and I'm going to put them on the balance. And let's say it reads 10 grams. And then I put all my red beans on the balance, and let's say they read 20 grams. And then I do the same thing with my brown beans. I put them on the balance, and let's say they had a mass of 5 grams. All right? Now, I need to know the average mass. I know the mass of all those beans, but I need to figure out the average mass of each bean. So that means I'm going to take the total mass of each bean, of each group, and I'm going to divide it by the number of beans. So the number of white beans by the total mass of the white. I'm going to take the total mass of the black and divide it by the number of the black. And then I'm going to take the total mass of the red and I'm going to divide it by the number of the red. All right, that's going to give me my average. So let's try that here. Let's see if I can get that done. Oh, crud. Hold on, guys. Okay, we're back. So I lost that data. Okay, well, let's say now, again, I can't remember what I said about these masses. So I have 1, 2, 3, 4, 5, 6, 7, 8 beans, and let's say that their mass was 10 grams. I can't remember what I said. And then I have 1, 2, 3, 4, 5, 6, 7 beans, and whoops, and we said that their mass was 20 grams. And then I have 1, 2, 3, 4, 5, 6 beans, and I said their mass was 5 grams. All right, so now what I'm going to do is divide those out, and that's going to give me my average. Okay, so this is average for the white, average for the black, and average for the red. All right, so now we have our relative abundance. So we're going to take our relative abundance, which was that percent that we got in the last slide, which I forgot what those values were. So relative abundance, and I'm going to multiply it by the average mass. So relative abundance of white times the average mass of white. Relative abundance of black times the average mass of the black. And the relative abundance of the red times the average mass of the red. All right, so that's going to give me 3 mass contributions. So relative abundance, stop punching buttons, Mondragon. All right, so relative abundance times average mass equals mass contribution. All right, so you need to do this for the white. You need to do it for the black. You need to do it for the red. And you'll have 3 mass contributions. So add all mass contributions. And when you do, you're going to get your average mass of beanium. So remember, your relative abundance is going to be in a percent. So if we say 20% of them had a mass of 0.5 grams, I can't multiply by that 20%. Remember, we're going to get rid of the of, change it to a times, and we're going to get rid of the percent by dividing it by 100. So that means I would multiply my 0.5 by 0.2. And that's going to give me my mass contribution. So I'm going to do that for each 3 of those, add them together, and then I'll have my average mass of the beanium. So again, see, does it make sense? Whichever one of these had the greatest relative abundance, that's the one that's going to be kind of in charge of the mass, right? Whoever there's the greatest population of, the average mass is going to be closest to them because there's more of them. All right, so what tomorrow is due is you need to finish up your data table. You need to calculate the average atomic mass of your beanium. I want to see all work, and pay attention to your sig figs. And then try some of those sample problems. So let's look at one of these examples that's off your homework sheet. Given the isotopes, and we're also given their relative abundance, remember that's in a percent there, and we're also given their masses. So we have the relative abundance of these 5, and we have the masses of these 5. Where are the masses? Those are the numbers at the top. So remember, we're going to put the relative abundance times the mass, and the average mass, and then we're going to figure out the mass contribution. So the first one says we have 8.0% of the isotopes of titanium have a mass of 46. 7.8% of them have a mass of 47. 73.4% of them have a mass of 48. And 5.5% of them have a mass of 5.5. Nope, I'm sorry. No, 49 it looks like. It's hard to see. 49. And the last one, 5.3% of them have a mass of 50. All right, so this is the relative abundance. This is the average mass. All right, so just like we did with the Bean Lab, we're going to multiply the relative abundance by the average mass, and that's going to give us our mass contribution. Now, here's the rules. We've got to get rid of the of, and we're going to replace it with a times. So I'm going to go through all of these, and I'm going to put our times in there. Now we have to get rid of the percents, and we're going to turn those into decimals by dividing by 100. So that means we're going to put a 0 there, put the decimal here, a 0 on the decimal. Now let's get rid of these decimals. All right, so we're ready to do this. Okay, so when I multiply the relative abundance by the average mass, I came up with these values, 3.7, 3.7, 35, 2.7, and 2.7. All right, now let's see what makes sense. We see that 73% of those isotopes had a mass of 48. We see the lowest mass is 46 and the highest mass is 50. So our range is 46 to 50. We have to fall in there somewhere. I'm going to predict that our average is closest to 48 than to any of those others because most of those guys fell into that average. So we had 73.4%. So these are all the mass contributions, and I got that again by doing the relative abundance times the average mass, and that gives us the mass contribution. So what I need to do with these is I need to add them all together. Okay, so I'm just going to do that real quick. And when I do that, I come up with 47.8, and that's the average mass. And that's what I thought, because remember I said this was the largest value, and so it had to be closer to 48 than to anything else. So 47.8 is much, much closer. So that's how you do it for all of those. You just have to find the relative abundance, average mass, multiply them. That gives you your mass contribution, and you add those together.